All right. So today we'll study concepts of virtual memory, right? So far we have studied memory, primarily cache memory. Okay, and we have also in the beginning lecture, first lecture, we have also studied about some aspects of disk, secondary memory, but we have not gone into details of how disk is organized. Actually, I will not cover that because very simple technology. There's hardly any concept in disk. You need to just understand how disks are actually organized. There are multiple disks in our hard disk. These are mechanical. We wrote, there's a motor to rotate that, and then there are concentric tracks, and then we and tracks are partitioned to sector, and we have to position head in the right sector. So disk we still use because contains a lot of data. So disk is very important. In last 20-30 years, yeah, disk have become very very important, and they are also improving in terms of technology, but we'll not get into any of those discussion in this class, right? So whatever we have discussed in brief, that's all, because it will take away one lecture. And this, I will send you PPT. I have already prepared the lecture some time back, and so I will send the PPT to you guys, and then you can study. We'll cover only topics that are really important and little complex. And one of the complex one is virtual memory. Okay, we'll look at uh, following topics. We'll look at what is virtualization. We look at also at virtual memory, then virtual address, physical address, how do we translate it, concept of page memory, page hit, and page miss. These are only some aspect we'll study today, and some other aspects we'll study tomorrow and then on Thursday. Now, please understand that what we have studied so far, we have made a lot of assumptions about it, right? When we studied pipeline, we have connected instruction memory and data memory. We have not bothered about the details. Only assumption we had was that within a cycle or sub cycle, we will have data available. Okay. Okay. So we will have data instruction available, or data available from that instruction memory, instruction available, and from data memory we can write or read data within a cycle. We have not bothered about organization, whether cache is attached to that or on main memory or whatever. We have assumed the ideal memory. Okay. All right. So, but today we will look at some details, and actually you'll have to visualize the whole thing. I mean, when you start your computer, up to the time your program start execution and program completes, what is the interplay of different components in computer system? Okay, once you can visualize each, then we can connect these things, because what we have done is that we have studied a lot of concepts in isolation. Now, of course, you cannot connect all of them until you study OS, which I think you will study in next semester, and then you should be able to connect all these pieces together. And as we discussed earlier, that OS and computer architecture has a great overlap. Okay, whatever we're studying now will be relevant in OS course. Like memory organization is again will be taught to you. Okay, so basically memory hierarchy, cache, concept of cache, then which was studied in great detail, and also virtual memory. All right, so we have studied so far very simple things. We have studied the concept of locality, which is very relevant in virtual memory. Okay, uh, if program has no locality, then virtual memory will also be of little help, right? We have studied temporal and spatial locality. Okay, and then we have studied this memory hierarchy. Okay, so we have not gone into detail how we get sorry, from disk to main memory, how do we do it, right? So we'll look at some of these caches. Then we have studied that, because we initially in our pipeline we assume that instruction memory and data memory, and these are very slow, because DRAM in general takes about 1000 cycles plus. Okay, so now if every instruction we we take 1,000 cycles, or every data fetch we take 1,000 cycles is too much, then our computers cannot speed up, right? So we have taken advantage of locality in program and data fetches. Okay, locality is instruction locality, is spatial and temporal locality, and brought all those things that are needed very often into a cache memory. And we have seen even cache is organized in multiple levels, and we have seen this organization. And top of that is of course the registers. Okay, so and then we have studied about the concept of the cache. That's something that is needed only can be brought in to the cache. All right, and then we have seen this general cache organization. Okay, all right. So now we'll get into virtual world, virtualization. What is virtualization in general, in your opinion?
So it's creating a notion of something that something exists, though it doesn't in actual physical.
Okay, good, very good, excellent, very good. Absolutely correct. So basically, we have concept of virtual memory, virtual machine, which you would have studied, at least used it, right? VMs we have created. Okay, what do we do in VM when we create VM? See, for example, I have Mac Pro desk machine, Mac Pro laptop, and that uses its own OS. Which is Apple OS, which is based on Linux or Unix. Okay. However, I can into this, I can if I want to do programming on, or I want to use say Linux OS, I don't need to partition the disk and create one VX. Um, sorry, create one VM for Linux. Sorry, I don't want to load Linux into it, right? In the hard disk. Instead of that, I can, on top of this OS, I can run a program, which is a VM, a virtual machine, and then that in that I can load whatever OS I want. Okay, so basically, what we are trying to create by virtualization is we are running and some kind of program which emulates the behavior of some other device, right? So so virtualization effectively is a process of creating software based on virtual representation of something. So basically something is there. Okay, so there is a system, and then we use some software on that and create, and it's something, for example, you know say as we have seen in case of VMs, underneath is something else. Hardware is whatever hardware it is, right? But on top of that we have one OS. However, whenever a request for something goes, we intercept it and create a version or representation of something else that we want. Okay, so is basically a process of creating a software based virtual representation of something, such as virtual application server, storage, and networks. Okay, see, prior to this virtualization came with something around 25 years back, it was very difficult to use multiple OSs in a system, right? And I remember sometimes in my second job, third job rather, in IBM, I first time I've heard of virtualization, where IBM AIX servers were able to also load OS, some different OS altogether. Okay, and initially when I was learning Linux, then I had created partition in my Windows machine and then loaded Linux separately. So all that is not needed anymore. Okay, so we can create virtualized version of anything that we want, and which is actually software representation of that. See, when we create virtual, say LAN, for example, now I'm not talking of VLAN, for example, we want to virtualize a link. Okay, so basically that representation also runs in the actual physical link. Okay, so we can create multiple such instances of that link, in software and actually put them on to work on the actual link. Okay, so we'll look at how does it, how this concept really applies to memory. Okay, and why do you want to make it virtual? What are we trying to do? See, so far when you are doing a programming, what do you assume? When you write a program, are you bothered about physical memory, or do you know even physical memory exists? No. I mean, ask a typical programmer who is non-computer science graduate. He may not know. He may know that computer has some memory, hard disk and memory, etc. But may not know more than that. Okay, because programming is just, you assume that the whole memory is available to you. Okay, so you don't even need to know what is address space, right? So see, initial systems when computers were designed, okay, they had just physical memory, okay, or main memory. When you use the word physical, it means that main memory. Physical is same as main memory. We'll use these terms interchangeably. And which is main memory consists of what? DRAM nowadays, right? Initially it was core some 30-40 years back. Forget about it right now. Okay, it was magnetic core in fact. So now this physical memory or main memory, there's a very simple system, right? Okay, and all embedded computers, microcontrollers or systems, use direct physical memory. So CPU, whatever say load store you do, okay, load store, you have to specify actual address, physical, okay, of the memory. So this is very primitive design, and however it is not. If it is just one application that's running here, like embedded system, in embedded system generally it's designed for one application, and it's very simple. All the control is with the CPU, and it can do, and it knows where what can be loaded and so on. Okay, but that's not the way most systems work today. Okay, see, your machine right now, my machine is running at least 50 different types of software. Okay, I may be running 3-4 applications right now, and I'm not bothered about where exactly in memory it's going and who's doing that, right? So this is this model with physical memory happened in earlier machines, earlier PCs and embedded system, but not anymore. Okay, um, but we visualize today an ideal memory. When in the beginning we started looking at memory, we visualize ideal memory, and that's what exactly programmer visualizes, right? It assumes that zero access time, this ideal memory. I mean, we can assume that whenever CPU wants something, is available. We don't see any delay most of the time, right? It has infinite capacity. Of course, infinite capacity we got with memory hierarchy, right? I mean, we studied this concept that disk is of highest capacity, and then registers as lowest, but speed is highest, right? And capacity goes up as we move down. That's the disk has highest capacity. So we visualize an infinite capacity available, which is very fast at very low cost. Okay, almost zero cost with infinite bandwidth. It means that multiple accesses can happen in parallel. So that's our idea. But in today's computer, in fact, assume some of these things and is left the internals to design inside it. For example, a typical high-end desktop must be running 100 plus processes, right? So these are the processes, 100 processes, and assumption is that there will be 100 memories. Each will have a dedicated memory, right? Because 100 processes 100 processes are using everything in memory, right? So they every each process will have uh, each process will reside in memory and also in cache. Okay, right now in our discussion today we are not discussing about cache, but cache and memory will use interchangeably. Okay, and we have seen cache to memory, main memory transfer happens automatically. Okay, so let's not right now worry about cache. We'll come to the cache little later. So 108 processes, but memory is just one, while each process wants its memory. So earlier assumption that we had was that there is one single memory like this. Now there are 100, here only one process running, it's fine. Now memory still remains one, but you have thousands of processes running. How do you do it then? Okay, all these processes have demand on this memory. Does it mean that each process should know what part of this main memory I should consume? No, they have no clue where it is, right? So they assume that they have what address space available. Each process has address space 00000 to some FFFF 32-bit. So 0 to 2 raised power 32 minus 1 memory locations are available. Every process will assume that. Then how will we share that physical memory across so many processes? That's the challenge. And that's where virtual memory comes into play. Okay. So the question that I may ask you is that when you execute a program, do you bother about main memory? Answer is no, you are not bothered about. Do you assume that all the memory is for your program? Yes, we assume that. Do you know what location in main memory your program resides? No. Do you know if full program resides in main memory? I don't know, but I want my program to be there, right? And do I bother whether my full program is there or not? No, I don't bother as long as my program does not halt or stops. Okay, and my response is good. It doesn't matter to me. Okay, what is your view about the address used in program or processes? I only know about what my program when I return is and compile it is there in is there in secondary memory or disk, and then when I bring it up, when I want to execute that, I know that OS creates a runtime environment for me, right? Which we have seen, like we have something called stack. We have also a heap, then static area, code area, text area, which we call, right, etc., etc., right? So we know that when my program is executing, okay, OS will create this for me, and it will have compiled code, or machine code available somewhere here. That's all we know. Okay, so now let's look at this way. Each processes at the runtime has simple layout like this, right? This we have studied. Okay, this address space that we have, we call it virtual address space, because see, each process assumes that it has all the memory available. Now we have studied 32-bit machine, right? So each process, then address space for this is from 0000. Each one is hexadecimal, so this makes 32-bit to FFFF, right, in hexadecimal. So these are 32. So this each process assume that this is the area available to me, right? So this is assumption. However, that's not possible, right? This is the view that process has, but it has to go somewhere in main memory, and or yeah. So not everything can be there, and how do you then map? Because process assumes that that's all it has, right? Each process has this view, then it has, and all this data thing that we see must go into main memory. Okay, and number of processes run concurrently. It means that physical memory or main memory is to be shared by a number of processes. Okay, and that thing we call it virtual memory, right? So how do we do it is essentially defines virtual memory. Okay, so the programmer has illusion of very large address space while having very small physical memory. Okay, so physical memory, can be smaller than the address space. Address space is how much? 32-bit address space is 2 raised power 32 addresses, which is 4 GB. Okay, main memory has been much smaller than this for very long time. Now, of course, now we have 4 GB kind of memory, like my laptop has 4 GB memory. Okay, but earlier this memory used to be very small, say, you know uh, 1/10 of that, 0.4 GB memory, or even less than that. So address space is much larger. That's a program can use 0 to 2 raised power 32 minus 1 addresses, but actually the space available, physical memory, is smaller than that. And that is only for one process we are talking. Now this physical space, physical memory, is to be shared by a number of such processes. All right. Okay. All right. So all this we have studied. So hardware and software cooperatively and automatically manage the physical memory to provide the illusion that each one is having full address space available. All right. Okay. So in addition to that, we also want something from main memory is virtual memory is when n number of users or processor using, each one should not bump into other, right? Or one should not steal data from other, should not write somebody else's space. So we want protection and we want efficiency, right? Because main memory is small and it has to be shared with number of processes, so it has to be used very efficiently. Okay, any question up to this point? Is it clear? Is it fine, or shall we? Okay, all right. So let's assume that you, because very simple things we have discussed so far, right? So let's understand what is address space. We have already discussed this earlier. So programmer has view only of virtual address space. Each process has a view of virtual address space, which is nothing but, if you have n-bit machine, so like RISC-V is 32-bit machine. Okay, so we have virtual address space of 2 raised power 32 minus 1. Okay, so basically 2 raised power and virtual address, including of course 0. Okay, all right. So these are the addresses which user program knows about, or each process knows about, right? So virtual address space is of course 0 to this one that we have discussed. Okay, and all modern system use 32-bit or 62-bit virtual address space. So we have studied only 32, but in RISC-V, but it can also be 64 bits. Most modern processor today use 64 bits. Okay, so that's about address space. Okay, it means so many locations a programmer can refer to, or his program can access or can reside in or access to so many locations. Now, then second thing is physical address space. Okay, note that in computers we have studied so far, we normally consider consider cache to be subset of it, right? So only thing that processor has visibility is that of a main memory. Now, and we know main memory is slow, hence we create hierarchy and um, cache, etc. But we are not bothered, about cache, because whatever address um, a CPU throws, it has to be honored by main memory, and then we can, of course, before going to main memory, we can check it from cache memory. Okay, all right. Now, so we have physical address space, that of a main memory. When we say physical address space, this is actual address. Physical is nothing but actual address in main memory, okay, which is DRAM memory. And we assume that P, okay, so is size is of that of a P, that is equal to 2 raised power P addresses, right? So basically we need P minus 1. So these are the addresses or locations in main memory starting with 0. So let's assume 0 starts here and this will be p minus 1. So we need p bits so to represent the address. Okay, all right. So while main memory, sorry, virtual address space, we have 2 raised power n addresses. So basically n is the size of virtual address space which program can assume is to be and mapped to say p uh, main memory spaces, right? If only one computer is using the physical memory, all right? So in fact, when there is access to any location in your program, it is to be mapped into the physical memory. We'll come to that. All right. So now we have this thing, we have a processor running, let's assume this is a process over a processor. Okay, it has view only of virtual address space because your program when you write is uses between 0 to say n minus 1. Okay, all right. This process, so each process will have this view as we have discussed, and at runtime it becomes something like this that we have also discussed, right? While we have single memory like this, so there has to be translation of virtual address to physical address. Okay, and that is role of a memory manager that sits in between. Okay, repeating, each process is running on a processor use only virtual address space because that simplifies thing for programmer, right? Programmer need not worry about actual memory size and where it will be. Okay, at runtime we have nothing but runtime simple layout. Okay, and then this is what a programmer knows about, right? And then or when we have when we did the programming in assembly, then the program has view of this one, and then this is to be mapped into physical memory with the help of memory manager. Okay, so each process uses own address space and process, so this is the address space. Okay, and each process uses this, all right, and wherein physical memory is only between 0 and whatever is ff whatever. Okay, depending on size of that. All right, so now let's come to the very simple mechanism. I'm repeating it several times so that it becomes clear. Address generated by each instruction in program is a virtual address. Okay, so it is not the physical address used to address main memory. Instruction uses only virtual address. Now address translation mechanism maps this address into physical address. All right, so it's something like this. We have program operates in virtual address space. Fine, this address space is taken and then the mapping is done. Now sometimes it's called hardware mapping. It's not truly pure hardware, it also has some software. Okay, but we call it hardware mapping, and then that converts into physical address. Okay, so when we use address in assembly language programming, in assembler architecture we use virtual address, and that is to be converted into the physical address at runtime. Okay, all right. So it is OS who can decide where it goes into physical memory. Okay, so we'll not look at that, how OS decides where to put something which or program or part of the program into the physical memory. We'll not look at those decisions, right? We'll study that in OS course. So conceptually at very high level, each process will get a part of memory. Okay, if there are n processes, or if there are, let's assume some large number of processes, not really n because we have used n for something else. Say we have some X number of processes. Okay, some of them may be in the memory. Okay, if they are all, let's assume that uh, let's assume at any moment there are only, at this moment there are only three processes in memory, three processes that are executing, and then three processes will use part of the memory. Okay, now this is the ultimate objective, that there has to be some separation. Okay, and it will be sufficient, whatever processor needs, that will be sufficiently available. So sufficient amount of memory should be available to the processor. Ideally it should have full address space available. Okay, so whatever process needs, it should be available. So we can also assume that this full address space available to it. However, that we know in practice that's not possible. So we'll look at the how we can implement. So real memory managers does more than this simple mapping, right? So we come to the concept of then paged memory. Okay, and today actually there are two kinds of virtual memory. One first is called segment based. Second is page based. Okay, so we'll study only page based because segment based is not in use. Only few systems use it. So when we speak of virtual memory, we speak of page memory. Okay, most all systems today, barring some embedded system, etc., that too I think also uses kind of page memory. Everything uses page memory. So we'll discuss only about page memory. Now we call main memory. Of course, when we say main memory, it also includes cache because cache is hidden to processor as physical memory. Okay. Now physical memory is broken into fixed size block called pages. So physical memory for us, for example, is 1 GB. Okay, then we can partition this into number of blocks. Okay, and say each block, typical block size is 4 KB kilobytes. Okay, so 1 GB is overall. So 1 GB divided 4 KB will be number of pages into the physical memory or main memory. All right. Uh, Simple. Sometimes some authors call this partition also as a frame. Okay, so if you get a word frame sometimes in the presentation or a book, treat this as a physical memory page. Okay, now processes use virtual address. Okay, and virtual address space is also divided into page of same sizes. Okay, so for a system, page size is kind of fixed. Okay, it's usually OS dependent process. So virtual address, if we have for example 32-bit machine, okay, then and we use say 4 KB per page, then virtual address space, okay, is divided into 4 KB pages. Now note that these are all, you have to just visualize it because actually it happens that there has to be some mapping for each page in virtual address space, but it may not exist. I mean, process may not use the whole address space. Okay, anyway, we'll discuss that later. So note that in 34-bit machine, it means that it is 2 raised power 32 address space, and each page is of 4 into 2 raised power 10. So essentially it is 2 raised power 22 divided by 4. That's equal to 2 raised power 20 pages will be there in virtual address space, and that is okay. And some of them may reside here. We'll come to that little later. Okay, just a minute. Okay, so we can visualize virtual address space as a virtual address which is of 32-bit is virtual page number and offset. So this so two we when we say 2 raised power 22 pages, Each one of these page will be represented by 20 bits that are here. And within that page, because we use byte addressable machine, so each one of the byte in the page is given by this offset number. All right, is it clear? Any doubt?
Can you repeat one more time?
Okay, so we have seen that address, in the process. Okay, in the process, when you have a process, we assume virtual address, right? 32-bit virtual address. When we did programming, we assume 32-bit address, right? When we did move something from one to other, then when we have that base register based addressing, right, we that base register of 32-bit. So 32-bit is the address that we have assumed. Okay, and what we are doing is that is a virtual address between 0 and whatever, 0 to 2 raised power 32 minus 1 locations. Now these, and what virtual address represents it, this whole thing goes to a location in memory. Okay, it points to a byte in memory. Okay, the whole thing. Okay, now we need to map this to main memory, right? In order to do a simple mapping, what we do is that we say that part of this is page address. Like in cache, we have block address and offset, right? Similarly, we have page address and offset. So 20 bits, we, for example, our case, we when we assumed 4 KB page, the first upper 20 bits can represent a page in main memory, and offset can represent which particular byte in, suppose this is the page, these 20 bytes bits represent the base of the page. Let's assume that this is whatever starting this way, address is going up this way, and then offset will represent how many bytes away it is from the starting of the page. Okay, so we can in this way point out the exact location. So that's what we assumed, right? Okay, uh, assuming that this is available, we never bothered whether it's a virtual address or something. We assume that whatever is there is available in main memory. Okay, but now because we assumed when we did our programming that only one process is running and all the memory is available, and we never bothered. But we are going a higher level where we know that there are multiple processes and my process will not get the full space. My whole virtual address is not, my whole virtual address space is not available in main memory. Okay, then what we need to do is that we need to map this into physical address. Then we'll have to first find out that this virtual address that I am using is available in main memory or not. Okay, in order to do that, how do you know whether this byte is available? If you don't create a hierarchy or some structure, then it means that you need to do mapping for each and every byte. Let's assume this byte is whatever, right? Starting say 32 bits, let's assume is XX, not XX, maybe some number 11101, 32 bits. Okay, 00, these are all 32 bits. This address processor wants to use. How do you know whether this is available in main memory or not? There must be something which will tell that this is available or not, because your main memory could be smaller than your address space or shared by many. So then you need a mapping of each bit, sorry, each byte in virtual address space and main memory, whether it's available or not. And this is very expensive. Imagine you are doing mapping for each byte. Actually, you need more than main memory to create this mapping, right? So what you do is that then you say that let me check whether whenever I make when I make a request for this, this will be part of a page, and page number will be given by this. Okay, because these are top bits, top 20 bits, and this one will give the offset. So whether this byte is available or not, I will check it later. First, let me find out whether this page is available or not. If this page is available, then I can get always whatever byte I want. Otherwise, I will have to bring that page from secondary memory to main memory. All right, you get the idea? Is it clear? Okay, so let's look at the, okay. So virtual page is mapped to a physical page in physical memory. So virtual page is actually, based on address space we have created virtually, we have partitioned into pages. Page size is the same that in memory. When we refer to a location in virtual address space, we check, we want to know whether actually this is available, the content of that is available in main memory or not. Okay. If it is not, then we bring it from the disk to main memory. Okay, so it's something like this, that now we have created, this is virtual address space. Okay, there will be some dot 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 in between. So this is a virtual address space, uh, which is nothing but 2 raised power 32 locations, and each is then we partition this into page, and let's assume page size is whatever. Okay, so this divided by page size is actually number of locations. So these are the number of pages. So we have so many number of pages, and then some of these pages are available in main memory. Suppose we want to refer to a location, we'll have to find out whether this corresponding to this location there is a page, because it will be part of a page, and whether that page is available in physical memory or not. Okay, so we need some translation mechanism in between, or which we call as page table. All right, and if it is not available, then it will be available in hard disk. Okay, then from the hard disk, we cannot read directly from the hard disk to CPU, so it has to be brought into the main memory. So we'll come to that later. Okay, so let's quickly go through what is page table. So page table is something that we need to translate these virtual addresses to physical address, or virtual page number to physical page number. Okay, uh, so virtual page to physical page we need. So this is a page table here. Okay, this is the one shown in yellow. Okay, so we get this virtual address from process. Okay, and then this is and page size is 2 raised power p. Okay, so we need p bits to represent a page. Then remaining bits n minus p is virtual page number. Okay, now for each process we have a table called page table. We know the location of that page table, the starting location from that's the base address of that page table. So this is page table, say for process, say let's assume some process number, say p1 we call it. Okay, we know the base address of that, and then from this one, this gives a page number. We know where we can see this entry, because there is one entry for each page. This is nothing but this gives offset from the base. Okay, and then we see whether this page is available or not. Now this is physical memory. Now whenever there is a page that's available, corresponding we will have a bit called valid bit, which is shown as a blue color. It will be set. Okay, so looking at the page number, we come here to page table and see whether page is available. If page is available, then we get the physical address, or the physical address of the page in physical memory. So we get this physical address, and then offset within the page is the same as offset for virtual address, and this gives a physical address, and then we go to main memory and read the corresponding thing. Okay, any question? Note that we right now it gives only partial picture. Any doubt up to this point? Okay, who can tell me? I only remember few names which are in the beginning. So I will ask this to Mandar Swami. Mandar, is it clear?
Sir, how is offset, like what is the role of offset there?
See, you get some address, right? Process is using 32-bit address. Okay. And then we say that 32-bit address, we have two partitions in that. Why we have a partition in between. Okay. A part of that represents, which is of 20 bits, represents page number. And the virtual page is mapped into physical page. Okay. And then within virtual page, because we are reading only a byte, right? Because we are using byte addressable memory. Okay. Then within that page, location of that particular byte that we want to read is offset in virtual address. Once we map this virtual page to physical page, so we take this virtual page number, index into page table and get mapping to physical page number. Okay, it means that that page of same size is available. Then we want to read some byte in that. Let's say the 10th byte in that. So that 10 number will come here. Then because page is available, then 10th byte in that is something that I want. So we'll use the same offset, which is part of virtual address, into take it here as an offset within physical page, because we mapping is between one page to another. Virtual page to physical. Note that we are not getting a byte from somewhere. Minimum replacement unit from whether something is available or not is a page. In cache, we have seen that we are we have a small part with 64 bytes available or not. We replace only 64 bytes. Okay, here we minimum transfer unit from secondary memory to main memory is a page. Okay, so basically whatever, even if you want to read a byte from main memory, the whole page has to be brought in. Whole page has to be there, right? So within that page, what memory location you want to read will come from the offset. Okay, all right. So same thing is represented. Forget about these numbers. Okay, this is actually for 32-bit, 31-bit machine for some reason. Okay, let's assume it's a 32-bit. So 0 to 31, and this is 20. Offset is 12. Let's assume for our understanding. Oh, all right. So we get this virtual page number. So this virtual address, which is of 32-bit, partition to is a 12-bit offset because of 4K page, and then the remaining are page number, virtual page number. We go to page table for that process, and that process will check whether the page which is given by virtual page given by these 20 bits are available or not. That page is available in physical memory. If yes, then we need to refer to that address in physical memory. How do you know about that address? This address, let's assume, is in physical memory. We get it, this address we create from this translation. Now this number of bits here may not be 20. If it is 20, then physical memory and address space size is same. It could be, say, this memory is, for example, 1 GB. Then we'll see 1 GB divided by whatever page size, we'll get number of bits here. So let's assume it converts into say 15 bits for some reason, let's assume. So take that 15 bits from this translation, and then we know that then this particular page is mapped into the page that's given by these 15 bits after translation. And then we want to read a particular byte in that that's given by offset, page offset. That page offset comes here then. Okay. So now with that and this understanding, let's go ahead and then try to see that how mapping happens for each process. Now we know that each process has its own address space, right? 0 to say n minus 1. Okay. Similarly for process 2 and so on. Each process will have then a page table for itself because it has large number of pages. Okay. You can see that 2 raised power 20 pages it will have. Okay. And then this page table will tell whether a particular page that is requesting or based on some address, virtual address. Let's assume process 1 is asking for a particular byte. Okay, from that we'll get the page number, virtual page number, and that virtual page number will index the page table, and then this mapping will tell us, and then there will be v bit, valid bit. If that is there, let's assume that this page is there shown as yellow, then we'll get from this one that address or virtual page. So we can go to this particular one page, and we go to the beginning of this page, and then using offset we can find out a particular byte within that. Okay, so this is a page table for process. This is a page table for process 2. This is a page table for this process 2, page table process 2, and there are some pages of that are available in main memory. Similarly, there are some pages for first processor available in main memory, which is shown as yellow. And if they are available, then valid bit is 1, otherwise is 0. So for example, this page is not available. The valid bit must be 0 for this one. And this is a one for third. Third process will have a page table here, and corresponding we can map it to main memory. Okay, note that the number each process is dedicated page table, and physical memory is non-consecutive. You may get first page mapped here, second page could be somewhere else. First yellow page, first page that in the process table is mapped here, second page could be mapped somewhere else, depending on how OS actually maps this to. All right. So basically what we have now is another view of that I've taken from different presentation. So each process have virtual address space. Okay, is divided into number of virtual pages. We are not bothered about offset now. Okay, and then each depending on this virtual address, virtual page number, we go to page table. Each process will have a dedicated page table, and in that page table we'll see whether the page is available. If page is available, it will map into corresponding physical page here. So we can get the physical page address, and we can go here and read whatever byte we want to read. And this is same is for the second process. Second process will also have page table, and will have entries will show whether the pages are available or not. Okay. All right. Any doubt about it? Any question?
Sir, these page tables are also in main memory.
No, we'll come to that later. Huh?
Okay.
Hold on to that.
Yeah.
Hold on, because you may ask that what is the page table size? For
Yeah,
our
it may
example,
exceed.
2 raised power 20, right?
Yeah, yeah.
2 raised power 20 entries are there. That each entry will have minimum 32 bits because it has, or approximately 32 bits, let's assume. The physical address could be smaller. So let's assume maybe 30 bits or maybe 25 bits or something. So 25 bits into 2 raised power 20 is huge memory. And will it is a way to keep it? See, very right question you have asked. Next thing is that can we keep it in the memory? Because first thing we'll have to check whenever CPU references any address, virtual address we get, we'll have to check whether the corresponding thing is available or not. It means that are we going to spend say 1,000 cycles to check that and then read it from, and then we'll get page address, physical page, go to physical page and read. So this is very expensive, right? So we'll come to that design later. Okay. Okay, so this is what we have studied just now. So OS keeps track of each process, whether it's active or not. Okay, and all active processes will have correct page table, or basically it will point to a page table. Okay, we'll look at data structure later. And the memory manager extracts the page number from virtual address. Okay, virtual address is known because this is what CPU generates. From that you extract the page number, look up the page address in page table, use this to reference the page table corresponding to that process because we know the base address of that. Okay, and use the offset. This physical page number maps into, sorry, virtual page number maps into physical page number, take the offset and have the actual byte address. All right, so this simple. Okay, another 2 minutes and then we'll stop. What happens if we assume that page is available in main memory? Okay, what happens if the page is not available? Then something is called page fault. Okay, when page fault happens, the virtual memory brings the page from disk to page in physical memory and adjusts the mapping. Okay, now this is the disk memory. We have not discussed the disk memory, so now we'll look at the structure of disk memory. Disk memory also corresponding to a process is partitioned into pages. Okay, now there are 3 different kind of pages it can have. First is that it is unallocated. It means that they don't exist. You know, a virtual, see, address space may have a corresponding page number, but you know, address space we not the process need not use everything. So something that is not there in virtual address will also not be there in disk memory. It may not contain anything, so it's not, it says unallocated. It means that these pages have not been allocated or created by VM system. Then there are something that we call is cached, which are there in main memory, right, or physical memory. So like something that's shown as blue. Okay, and something that is available because part of address space, but or it's the, but it has not gone into physical memory. When we say cached here, cache means does not mean it goes to cache memory. For secondary memory, physical memory works as a cache. When we say cached, it means that it's part of the main memory. So when we say cached, it means that it's a part of the main memory. Note that all this we are talking with respect to a process. Okay, so there are 3 types: unallocated, which don't exist in secondary memory, although there may be entry somewhere in the table. Both there will be entry both in address translation table that we have studied just now, and also somewhere in secondary memory. And there the cache, these pages are there in main memory. And uncached means that something exists here corresponding to address space, but OS has not brought those pages into main memory. These are not in the memory. These are the simple mapping. So just another 1 minute and then we'll close. So this is the physical. Now we assume that page table is in physical memory. Okay, and the entries of page table we call as PTEs, page table entry, and it maps virtual pages to physical pages. That's we have already studied, right? So now we have 3 kinds of entries in this page table. First is null. It means that these are not allocated. It's not using anything. Then something that's available. Okay, so it will map to corresponding physical memory, and something that has not been allocated it will map to say for example somewhere here in the secondary memory. So this page table entry will have null. It means that nothing is that page we are referring to is not there, or something that's there and corresponding address here will give the physical address or page address, page number of physical memory. And if it's not allocated but exists, then this address, these bits here will corresponding to address page number in disk memory. Okay. Now next thing that we can do is that if there is a page hit, that case we know that whatever address we are using that's available, the page number is available here, corresponding physical page is available here, then we can directly go here. If it is a miss, then we can bring the page fault or miss, then we can read the page from here and bring it to main memory. All right. So these three cases we'll discuss in the next class. All right. Okay. This is very important concept. Very important concept. It takes a while to understand it, right? It's not trivial. That's the reason I try to split it. First, consider the mapping between virtual address to physical address, and then bring in the concept of memory, and we'll combine this in the next class. Okay, and then we'll see how actual cache really fit into the whole game. Okay, all right, any question? Please please spend some cycles to understand it. Okay, at least half an hour you should read it from PPT, also from the book. Okay, and most books contain this concept. This is considered as one of very important concept in computing. We have seen how cache memory, that's another important concept, and then virtual memory. Okay. And of course there are other things that we have studied. So there are only, I would think, 10 or 12 main concepts in computer system which are important. This happens to be one of that. All right. If please go through book and PPT again and try to understand. If you don't understand anything what we have discussed so far, please bring it in the next class. All right. Okay. Thank you. Any question, please feel free to ask.
Sir, do we use this memory virtualization for all the processes which run on our normal OS or only for virtual machine?
No. So how will it see how many processes you are running on? What are you using now? Laptop?
Phones now.
You're using phone, right? How many processes are running right now?
Many, sir, like each like at
There
least
must be at least, if you in Linux you can see actually number of processes running, but here also there must be, you're running at least 30
10, 20.
processes right now, 30 to 40 processes minimum, because OS is also running processes. You're running then this system software that's running also. There's not just one process, maybe 30, 40 processes. So you have so many processes running on mobile as well as in desktop, right? Each cannot,
Yes.
who is doing this, whatever you're running now, you may not run after 10 minutes. Okay, so it means that each and every process in all modern processors use virtual memory concept, until unless you have embedded system in your refrigerator that using just one task, then you don't need all this, right? You know that what all tasks to be done, and it can be placed in main memory. All right.
Okay, sir.
All right. So in many modern system, see, the usually physical memory is smaller than address space. Now, of course, we can have same size, even more than that. But that physical memory is shared among a large number of processes at any point in time. Okay, then of course your virtual address space has to be mapped into physical address space. So everything that you do in any processor today, unless until it is embedded processor, it has got to have virtual memory. Because of who will provide protection in your system? If it's shared with somebody, then anybody can read. You know, you are running right now Zoom, right? If Zoom can read your bank details, then you are gone, right? So you know, so why? So you know, the whole thing has to be then mapped into separate pages. You know, so each process will have certain number of pages which will be distinct from distinctly mapped from that for other process. All right. Okay, so think about it, and then we'll discuss this in the next class. All right. Thank you.